Superparamagnetism is the magnetic behavior of very small ferromagnetic or ferrimagnetic particles. Here, the entire magnetic moment of a nanoparticle acts collectively as a single giant moment, but one that randomly flips direction due to thermal energy. In a macroscopic ferromagnet, the material divides into multiple distinct magnetic domains to minimize magnetostatic energy. Shrink the volume to the nanometer scale, typically 10 to 50 nanometers, and creating internal domain walls costs too much exchange energy. The walls vanish. The lowest energy state is now a single magnetic domain. Inside this tiny volume, thousands of quantum spins align perfectly, acting together as one unified unit. Yet, despite this rigid internal alignment, the particle fails to act like a permanent magnet. Remove the applied magnetic field, and the magnetic moment does not stay fixed in one direction. To resolve this, we have to split the physics into two layers. First, we use quantum mechanics to explain how the massive internal moment is built. Then, we use statistical mechanics to understand how thermal energy randomizes it. Grasping these two opposing forces explains why nanoscale magnets break classical rules. It establishes the absolute physical limits for both magnetic data storage and biomedical engineering. The foundation of all magnetism is the electron. Every electron possesses an intrinsic quantum angular momentum, known as spin, and an associated magnetic moment. It acts as a tiny quantum magnet. In magnetic solids, neighboring electron spins interact through a completely quantum mechanical process called the exchange interaction. This force arises directly from the Pauli exclusion principle, combined with electrostatic repulsion. This quantum Hamiltonian defines internal alignment. The operator Hx calculates total exchange energy by summing interactions of neighboring spins. The key variable is the exchange coupling, J. When positive, parallel alignment lowers the energy, the spins lock perfectly together. By summing all these locked atomic spins within the single domain volume, we generate a total collective magnetic moment. This is the superspin, mathematically defined as the saturation magnetization multiplied by the nanoparticle volume. Therefore, the particle does not act like a loose cluster of atoms. It functions as a single, massively scaled quantum magnet, thousands of times stronger than an individual electron. But this superspin cannot rotate freely. Real crystals possess structural preferences, meaning the magnetization favors specific alignments called easy axes. This directional preference is caused by spin-orbit coupling. It physically anchors the direction of the electron's spin to its orbital motion, which is tied directly to the crystal lattice of the nanoparticle. For a simple uniaxial nanoparticle, this graph models the energy landscape using the equation E equals kV sine squared beta. This creates a double well potential curve. The energy is lowest at angles of 0 and pi. These are the two stable minima, where the superspin prefers to rest. Between these two valleys lies the hard direction. Reaching it requires overcoming a strict physical energy barrier equal to K, the anisotropy energy density, multiplied by V, the particle volume. In a macroscopic block of material, that volume multiplier makes the barrier immense, trapping the magnetization permanently in place. But scale the volume down to a nanoparticle, and that barrier shrinks dramatically. At temperatures above absolute zero, the superspin is constantly bombarded by ambient thermal energy, defined as Boltzmann's constant times temperature. Because our nanoparticle volume is so minute, the kV anisotropy barrier drops to a scale comparable to the ambient thermal energy pushing against it. The Néel relaxation law calculates the time for the moment to flip over the barrier. It's an exponential relationship, with barrier height kV divided by thermal energy. Reducing particle volume slightly causes the time between flips to plummet. The internal quantum spins remain locked together, meaning the particle is still internally ferromagnetic. However, the collective superspin vector is now being violently kicked back and forth between the easy axes by thermal fluctuations. This thermal flipping continually randomizes the direction of the magnetic moment. Externally, the permanent macroscopic magnetization is erased, leaving an object that behaves statistically like a single paramagnetic atom. So how does this rapidly fluctuating superspin respond when an external magnetic field is applied? For an ensemble of identical, non-interacting nanoparticles, we map their collective magnetization using the Langevin function. This chart compares an ordinary atomic paramagnet against a superparamagnet. Notice the steep, aggressive climb of the superparamagnetic curve. It saturates rapidly, even under very weak applied fields. Looking at the low field approximation of the Langevin function on this curve, we see exactly why. The magnetic susceptibility scales directly with the square of the particle's magnetic moment. Squaring the moment has massive implications. If an ordinary atom has a moment of 1 Bohr magneton, and our nanoparticle has a collective superspin of 10,000 Bohr magnetons, squaring that difference amplifies the material's magnetic response by a factor of 100 million. That squared scaling defines the super in superparamagnetism. It yields a material that reacts to applied fields with the violent strength of a ferromagnet, but immediately randomizes to zero remanence the second the field is turned off. Whether we observe this superparamagnetic behavior or see a seemingly permanent magnet depends entirely on the timescale of our measurement. This introduces the blocking temperature. It is the exact thermal threshold where the average time it takes the superspin to flip matches the time it takes the laboratory instrument to measure it. This derivation takes the Néel relaxation equation and sets the relaxation time equal to the measurement time, isolating the temperature boundary. This solved formula reveals the direct relationship between particle volume, anisotropy, and measurement duration, resulting in a standard laboratory estimate of kV divided by 25 times Boltzmann's constant. A particle is not intrinsically a permanent magnet. It only appears to have permanent remanence, becoming blocked, if your laboratory measurement occurs faster than the particle's thermal flip rate. Engineers rigidly exploit this blocking temperature boundary depending on what a technology needs to achieve, starting with systems designed to operate above it. In biomedicine, superparamagnetic iron oxide nanoparticles are frequently injected into patients to enhance contrast during MRI scans. Operating above the blocking temperature is biologically mandatory. The massive Langevin response gives the MRI machine a strong, clear signal, but because the particles retain zero remanence once the magnetic field shuts off, they don't attract each other and form lethal clumps in the patient's bloodstream. Conversely, high-density computer hard drives must operate strictly below the blocking temperature. For a magnetic bit to reliably store data, its relaxation time must massively exceed the measurement time. It needs to remain stable against thermal fluctuations, not just for fractions of a second, but for over 10 years. As engineers continually shrink the volume of these magnetic grains to cram more terabytes onto a disk, they lower the energy barrier. Eventually, that barrier drops precariously close to ambient room temperature. Past this threshold, known as the superparamagnetic limit, and the ambient thermal energy of the room will spontaneously flip the moments, instantly wiping the drive's data. Superparamagnetism sits at the exact intersection of quantum mechanics, thermodynamics, and information theory. It dictates the absolute physical limits of nanoscale technology.